All right. And we're now hearing from Martin from Mission Critical Applications on a particular intriguing topic, which is seL4 on Arm Morello, which of course is the implementation of the CHERI capability system.
Thank you, Gernot. Good afternoon, everybody. It's very nice to be here. My name is Martin Atkins. I'm from Mission Critical Applications, which is a very unusual thing in our industry. I think it's a family business, which I run with my wife, who unfortunately couldn't be here today. She didn't get a visa interview quickly enough to be able to attend, but she would have liked to have been here. So I'm here to, as I said, talk about CHERI and seL4, and I assume most people here know more than they want to hear from me about seL4, but CHERI might be a little bit different. In the middle here we have a poster we prepared for a previous event, and the little picture at the bottom really sort of summarizes the way we see things. We see Morello's the cupcake at the bottom, and then we have seL4 as the icing, and then CHERI is sitting on top with the applications. And that is how we like to think about this. So first of all, well, what is CHERI? CHERI came from Cambridge University in combination with SRI International. And CHERI stands for Capability Hardware Enhanced RISC Instructions, which basically means that CHERI adds capabilities to the hardware of well, the name suggests only RISC processors, but actually I think that's because it made a nice acronym. I don't see any particular reason why it's limited to RISC processors, except that they might make something simpler. But it's unfortunate in this community that capabilities are a fairly widely used word, and it has a somewhat different meaning in this context, although the traditional meaning in the industry. So basically what CHERI does is it protects a process from abusing its own memory. And that's in contrast to what we've heard up till now with seL4, which largely protects processes and protection domains from other processes and protection domains. And I'll go into that in more detail as we go on. So then the other half of the story is Morello, and Morello is Arm's prototype implementation of CHERI as an extension to the AArch64 architecture. So there's some history involved in this effort. In fact, there's a parallel effort that started somewhat before us in the US, and DARPA and Trusted Science and Technology have been doing some work in this area as well, but they are a bit limited in what they're able to say at the moment. I've got some slides from them a bit later on, which they've been kind to give me to update you on what they're doing at the moment as well, but we'll come back to that later on. The work that we've been working on actually originated in Arm Research last year, where Sid Agrawal, who's here, and did a lot of the initial work getting things running on the Arm Morello platform. And he only had limited time, and we basically sort of started from where he left off, and that was a very good starting point for us. We started work in autumn last year, working from that code on a funded by Digital Security by Design, which is a huge government, UK government program that has supported the development of the Morello chip and a lot of other work done to try and improve the Morello architecture. And they had a program called Technology Access, which enabled us to get hold of hardware and access to some expertise from the community that helped us to get where we are. And we're currently on a project with UK Defence and Security Accelerator, DASA, which is helping us to progress that work a bit further. That's run by DSTL, which for the Americans here is sort of the UK equivalent of DARPA. And my reason really for going through all of this is to give you some idea that there's a fair amount of sort of government support behind all of this in the UK. It's seen as quite a strategic way forward in trying to achieve cybersecurity, or improve cybersecurity, should we say. So, a bit more background. The Morello chip is an industrial prototype. It's a workstation class, a demonstrator, SOC, and as I said, was developed under this government initiative. It's a pretty big chip. You can see the picture there of the package, and it's based on the Arm Neoverse N1 version of the Arm architecture. Unfortunately, that means it's not really appropriate for embedding in little IoT devices and small things you might want to have experiment with in embedded systems. But we hope that we'll get more hardware that's more suitable for that area later. So going back to the capabilities, essentially what CHERI does is it replaces pointers by these capabilities. And that means that it adds permissions, bounds, and lower bound and upper bound to what we normally think of as just a virtual address. And this allows the CHERI hardware to detect and disallow the illegal uses of pointers. It can check a pointer against the area of memory that that pointer is intended to be able to access, and it can do that at runtime with little or no overhead actually during the normal execution of the program. However, this does require the code of the program to be recompiled for a number of reasons, which I'll come back to at the moment. And it allows you to do other interesting things, such as hardware enforced compartmentalization, where you can split an application up into several different protection domains and isolate those protection domains from each other in much the same way as seL4 isolates different protection domains from each other at the operating system level. That isn't something we've worked on yet, but that's something that is the subject of a lot of current research at Cambridge, because they regard the basic functionality as being more or less done now. So a CHERI chip has two modes of operation, and those are associated with two modes of compilation. There's one mode which is called PureCap, which is where every memory access through a pointer goes through the CHERI rules and will potentially cause a trap if it doesn't meet those CHERI rules, either because a protection bit, maybe you're trying to execute and the execute bit is off, or maybe you're outside the bounds of the pointer. There's a second mode called hybrid, and this causes some confusion. In hybrid mode, the normal instruction set is exactly unchanged, but the additional instructions or variants of the instructions are added to enable you to manipulate capabilities and dereference things by capabilities, dereference pointers, capabilities that you have. Now, that is most useful in low-level code and code in the operating system, fairly obviously. And it's useful for sort of setting up the capabilities for other parts of the system. And it's useful when the code that you're working with is quite difficult to meet the requirements to just push through the PureCap compiler. The gold standard is to try and compile everything PureCap, but sometimes that proves to be too difficult. So So going into the capability in a bit more in a sort of pictorial way to make it more concrete. So we have a normal pointer operating above, and we have a 64-bit pointer, 64-bit architecture, and the pointer just contains the address of a byte in memory. With a CHERI capability, all the registers and all the pointers become 128 bits in memory. In fact, that's a slight lie. There's 129 bits, which is a bit odd, and you might well ask, where does the 9th bit come from? The 9th bit is actually held in completely separate memory, which is accessed in parallel to the main memory of the system, and is thus protected from normal access by any operation that the normal instruction set can do. Although, of course, there are some special CHERI instructions which enable you to do limited things with the tag bit. But basically, the tag bit says whether the 128 bits it's associated with is a capability or not. If you try to dereference a capability that has the tag bit unset, it will trap. You won't be allowed to do it. And if you dereference it with the tag bit set, then it goes through the bounds check and the permissions check, and you can see that this access would succeed because it's in the allowable range. And that 1 bit is also there in registers. I'll just add that. And when you move a value from memory into a register, the tag bit will get copied at the same time. So that's a sort of overview of CHERI. Just to be complete, I'll put an overview of seL4, but I don't think there's any need to really go through that in this audience, so I'll just skip over that slide. So we've touched on this at the beginning, but the big question is always, well, why CHERI on seL4? And our take on this is that seL4 provides guaranteed isolations between user tasks using proof and memory protection, with, of course, strictly controlled communication, which makes it useful. Whereas CHERI sort of saves a user process from itself. When somebody breaks into a computer, or a hacker breaks into a process, the normal first step is to get outside the little space they've broken into the rest of that process. And that is the first step of any bounds any attack on a system that uses an absence of bounds checking. So we see that seL4 can bring to CHERI a proven trusted computing base with all the advantages that everybody here knows about. But CHERI can also bring to seL4 a safer and more secure user space, which is the area which seL4 itself doesn't directly address, although it does address in the ways of helping people to write good code that we've discussed in the last couple of days, but it doesn't address in a sort of technological way, and also those sorts of things don't really deal with the vast amount of legacy software that we might still have to deal with for, unfortunately, quite a long time in the future. So in more detail, the seL4 kernel is proven, so we don't think there's very much to gain by thinking about using CHERI capabilities inside the kernel. But as we move out of the kernel, the system services are usually not proven. There are some counterexamples, but most of them are not proven. And also the applications are not proven. And we see both of those as places where CHERI can provide some benefit for very high secure systems or highly safe systems. Now, it's interesting to note that Rust also provides similar types of guarantees to CHERI. The main difference, I think, in principle, is that Rust provides those guarantees at compile time, whereas CHERI does it at runtime, and that's always a good advantage to have. But unfortunately, the world being the way it is, Rust isn't going to be used for everything overnight, however much we might want that to happen. There's legacy, There are other reasons why some organizations might not be able to use Rust. They might not have the expertise in-house. They might have large code bases that they need to be able to work with and so forth. So the future might be different, but we've got to deal with a more immediate future when things might be more complicated than that. So this is how I see a system working with this combination. We have our seL4 kernel at the bottom. We have a group of system processes on top of that, including a virtual memory manager. And then we have user application processes above that of varying criticalities. And the goal is that every process within this, or every protection domain within the system, we have a choice between whether to compile that part of the system or that process with PureCap code or with hybrid code. There's also this third possibility of Rust, and we see no reason why we can't mix and match any of these as is appropriate to the sort of guarantees that we're looking for, the sort of criticality of the system and the cost-benefit analysis of putting the effort into converting or doing what's necessary to compile code to use CHERI capabilities or not. I should add, I'm making that sound worse than it really is. Most modern code compiles to PureCap with, I think it's 1 or 2 changes per 100,000 lines of code or something like that is the sort of statistics that they're coming up with. But if you look at low-level code like memory allocators and things like that, then that takes a lot more effort to get right in the CHERI system. So it tends to be low-level system libraries that cause the problems, but unfortunately those are needed for the higher-level things to work. So there's always a cost-benefit trade-off that we can choose between these different approaches. So this is our, not roadmap, but underground map of where we think the project is and might be going. This is how we found the project when Sid left it to us and we started. And you can see the little trains on the left-hand side. We hadn't quite reached a stage where we could run programs in hybrid, run an seL4 hybrid user space application, and we were running on CHERI on the QEMU emulator. So now things have moved on a little bit, and we can now run the whole of the seL4 test suite in hybrid user space, and we're working through some other examples through the tutorials and other things from that are of interest to our sponsors. And at the bottom, we've moved on, and we have a choice of whether to try and use the ARM FVP emulator as an alternative to QEMU, which we're told is a good first step towards working on the Morello hardware. So things are moving on. We're just under halfway through our current project. So we're hoping to reach somewhere just before PureCap, before the end of this project. But these projects are notorious for not going to plan. So some changes to seL4 are obviously necessary in order to make this all work. Obviously, we're trying to minimize the changes as much as possible. We're very much aware of the impact of any changes on the verification of seL4, and that is something we don't want to unnecessarily make more complicated now or in the future. However, there are some changes that are absolutely necessary. The system initialization code, which of course probably isn't actually part of the proof, but this is seL4 in general. I haven't put a dotted line around which bits are proven and which aren't. That might be an interesting exercise for later. But the several architecture registers have to be used differently. page tables have some extra permission bits to deal with capabilities, so there's a little bit of change in the page table management code. CHERI can generate faults which aren't present in a normal AArch64, so there are some changes there. There are some extra bits and modes and things in the program status register. Going up to the user side of the user space side of things, all the registers are 128 bits. So the context switch code has to obviously save all 128 bits, not the 64 bits it was written for. And we need some changes to the IPC mechanisms so that we can communicate down to the changes in the fault handlers and the page tables and so forth. The thing that was surprisingly awkward and caused most of the problems was actually there are two special registers which are used for hybrid mode called the DDC and the PCC. And basically these are the sort of God capabilities that give you access to the whole machine and from which you can generate the smaller capabilities that you want to give out to user processes or parts of a user process. And somehow those have to get from the hardware to the user processes. And so that's the tall blob on the left. Then there are lots of interesting questions about what else one might do with the caveats of trying to make the minimum changes possible. And more on that in a moment. So this leaves lots of open questions. Perhaps the biggest fundamental question is, are these two, is how CHERI capabilities are managed in this sort of system. In seL4, the whole idea is that most of the management is done by other user processes, and we would like that to be the same with CHERI capabilities, but that means we have to have some way of communicating CHERI capabilities. CHERI capabilities are virtual addresses, so we have to be careful with shared memory. And so, and related to that, we have to decide how CHERI capabilities are best communicated and how they're represented in messages. Should we integrate them into the permissions mechanism? And currently, we've done a rather ad hoc mechanism of just trying to get something that works so we can get an idea of what we might like to do differently. And then there's a question of, is there anything differently we might like to do for dynamic systems? So all through this, we're bearing in mind the work on verification and scoping the code changes. There's the opportunity of both of informing the changes that we make from the proof effort that we think might be needed to repair the proof, but we don't really want to restrain the R&D effort either at this point. So right now we're trying to get something that works, and then we'll revisit it and analyze each change to see if it's necessary, if it can be done better, and what the impacts of that are. We talked a little about certification earlier, and we're interested in getting something that can be certified. We're coming from, our sponsors are currently from the MOD, so they're obviously interested in certification. And there's a verification branch line on our underground map that we've just got some ideas about how verification might proceed in this environment. So now we've got a couple of slides from our colleagues at DARPA and Trusted SC. If you have any questions about these, I suggest you talk to Yacht Clan, who's over there, and his team. I would just quickly run through them and give you some idea of what they've been doing. So they have got slightly further than we have because they started earlier. They have a CHERI-aware seL4, and they have built on top of that security services and a system interface, which enables them to enable CHERI capabilities in user space. And they've also got the VMM code working under CHERI, but I don't believe that the capabilities are actually visible in the in the virtual machine, but that's an interesting question that we could discuss. But essentially, their approach is to keep seL4's role as being the same as it currently is, which is similar to ours. And they've taken an approach of using a shim layer to leverage the capability model and reduce the impact on seL4, and then use that to cherify the security services on top of that. And they've got an integrated end-to-end workflow that's working for them at the moment. And this has been developed for a particular demonstration, which I believe they're working on at the moment. And this is a screen dump and photos showing their development system. And they've also got the seL4 tests running, as you can see. Well, you would be able to see if it was legible from that distance, but that is the end of the seL4 test run, if you believe me. So in summary, we think that seL4 and CHERI are complementary and both can add to the security of a system. Porting seL4 to Morello is much like porting to a new architecture, but fortunately it's one that's very similar to Arch64. The changes are very, very tiny in comparison to the full amount of code for Arch64. But it's early days yet, and further work is needed to make the best of this combination. And there are lots of interesting research questions that can be looked at as well. Although our real first goal is to get something that is actually usable, and then move on to some of the more interesting stuff after we have proved the concept. So just a few acknowledgements to everybody who's supported us, and Sid, who got us going, and Nick has given us some support with seL4 as well, and Paul is giving us some advice, and my daughter has got involved as well, and she's doing some of the graphics design. So it's really been a family effort. So thank you very much for listening. Stunned silence.
Are there any performance overhead when dereferencing a pointer in the PureCap mode?
Very little. All the checks are done in parallel to the normal stuff that's happening anyway. So there's very little extra overhead. There has been some measurement, but it's very... The real overheads come from the extra things you have to do to manage the capabilities rather than the runtime overheads of using the capabilities. And even those overheads are relatively small. But I can't put particular figures on them, but there's been a lot of research done by Cambridge if you want to have a more definitive answer to that. They have papers about the runtime impact.
This is, I guess, a question about how would you use CHERI capabilities with seL4 capabilities. So if you have a CHERI-enabled application on seL4, it has its C space, and you call into some partition of the code with a reduced set of capabilities, how is that part of the code expected to potentially make a protected procedure call, something like with an endpoint, or access a invoke an seL4 capability?
That's a very good question, and that comes into the questions of how we communicate capabilities in the best way between seL4 protection domains. One possibility is that we'll start out by only allowing certain system tasks to do that, and then we'll try and work out how to build that into the permissions mechanism. There are several different competing ideas about how to do that, and we're still trying to evaluate those to see how best to go forward on that. That's sort of research in progress, I would say, at the moment.
Just to follow up on this one, it seems like there's really two ways to do protected procedure calls. There's intra-process, where you invoke a CHERI cap, or or a gateway through a CHERI cap, and then there's the traditional seL4 IPC. Can you see that being abstracted away so it's transparent to the application?
One of the first questions that Sid addressed when he was looking at this was, what's the relationship between these two types of capabilities? And I think his answer was they're both the same English word. And I would agree with that. I think to begin with, at least, we're thinking of CHERI capabilities as being more useful within a protection domain than across protection domains. There are other clever things you can do with capabilities that I haven't talked about. You can seal a capability so that it can't be used until somebody comes along with the right capability that's a key. And you can do things like, that can be used to do things like communicating things through untrusted parts of the system where they can be unsealed by the receiver on the other end and things like that. And all that can be done within a single address space. So you can compartmentalize your address space by capabilities as well. So in the very early days of capability machines, people were talking about single address space machines. And a lot of the ideas from that are coming back, but all within one seL4 protection domain. So we have the possibility of having both worlds coexisting. I think there are lots of interesting questions, but we certainly don't have all the answers at the moment.
25 years ago, I would have killed for such an architecture. We were doing single address space operating systems.
I can certainly second that.
Any other questions? Yep.
So I take it when you compile the seL4 kernel itself, that CHERI protections or capabilities are turned off. Is that right?
They're not turned off. It's compiled in hybrid mode,
Okay.
which basically means that unless you annotate your source to say something's a capability, then it isn't. So the approach has been to, the seL4 kernel is just using the normal AArch64 instruction set, but then there are a few additions that we've had to put in, as I described on that slide, and in those particular places, there are annotated bits of code which actually manipulate the capabilities. But the main seL4 operating system is compiled essentially with them turned off, but in fact, that's not actually in practice what happens. It's indistinguishable from them being turned off.
So how many of those annotations did you have to do?
There are I think the total number of changes throughout the entire seL4 system are in the small hundreds of lines. But some of those changes are just to comments and things. So don't take any of these numbers as very definitive, but it's very small in comparison with even the AArch64
The trick is just
code.
knowing which hundreds of lines that they are.
It's always the case that knowing which is a much bigger problem than actually making the changes, as we heard in the previous talk.
Okay. Any final question? No. Then it's time for our last break.
Thank you.